Video 66 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is couple cluster theory. The couple cluster wave function is obtained from the Hartree-Fock wave function by applying an exponential operator, where the exponent in the exponential operator is called the cluster operator, and it's the sum of all the excitation operators as we have defined in the lecture on excited determinants. So it's the sum of all the single excitation, double excitation, and so forth, and tuple excitation operators for an n-electron system. And here we should remember that, for example, the T1 operator is the sum of excitation, all the single excitation operators multiplied or weighted by some expansion coefficients Ti alpha. So when acting on the Hartree-Fock wave function, it will generate all the single excited determinants weighted with these expansion coefficients. And similar for the T2 operator, which generates all double excited determinants. Now the expansion coefficients Ti alpha, Tij, alpha beta, and so forth, in couple cluster theory, they are called singles, doubles, amplitudes. So here they are called amplitudes. Different couple cluster methods are obtained by truncating the expansion of the T of the cluster operator. If you use the full cluster operator, meaning up to n-tuple excitation, then the couple cluster wave function actually is the same as the full CI wave function, and therefore the exact wave function in the space of a finite basis set. A popular couple cluster model or method is the so-called couple cluster singles and doubles model, where one truncates the expansion of the cluster operator after the doubles excitation operator. So it includes the T1 and the 2 operator. Now one inserts then the couple cluster wave function in the Schrödinger equation and then gets what sometimes is called the couple cluster Schrödinger equation. If one uses the full cluster operator, then this is not an approximation to the Schrödinger equation, just the Schrödinger equation where we have inserted a particular form for the wave function. The question is now, how do we get an expression for the couple cluster energy then, and how do we get some equations from which we can determine the amplitudes? Well, it's actually done very much the same as in Møller-Plaisset perturbation theory. It is done by projecting the equations against the set of Slater determinants made from the Hartree-Fock spin orbitals. If we can look at this, so we project on the left here against the Hartree-Fock determinant, which this then gets this transition expectation value of the Hamiltonian, and on the right-hand side, because the energy is a constant, we get an overlap between the Hartree-Fock and the couple cluster wave function. But the Hartree-Fock wave function is, of course, orthogonal to all the excited determinants, so the only term which contributes from the cluster operator acting on the Hartree-Fock wave function is the Hartree-Fock Slater determinant, and because it is orthonormal, this gives one. Project the equation against the Hartree-Fock Slater determinant, the SDF Slater determinant, then we get the couple cluster energy. And if we get, therefore, the couple cluster energy. So the couple cluster energy we obtain by projecting against the Hartree-Fock determinant. We could also, and that's often more advantageous, project not just against the SDF Slater determinant, but the SDF Slater determinant where we have pre-multiplied with e to the minus t. So we pre-multiply the equation on both sides with e to the minus t and then project against the SDF Slater determinant. This still gives just the couple cluster energy. Now, equations for the amplitudes one can obtain by correspondingly pre-multiply the equation with e to the minus t and then project against single excited determinants, double excited determinants, and so forth. Where if we project against the single excited determinant IA, then we will get an equation from which one can obtain the amplitude corresponding to this single excited determinant and correspondingly for the double excited and so forth. As I said, this is very much the same as one does in Möller-Blessed perturbation theory. Now the right-hand side of these equations, as I've written here, they all vanish, so it's all zero. And let's have a look at how this happens. So I have on the right-hand side, I have the energy standing, which of course I can take out of the integral. And then I get an integral, which is the Cover cluster wave function pre-multiplied with e to the minus t, and then some excited determinant here written with our de-excitation operator, which when acting on the artifact determinant in the bra, of course, becomes then an excitation operator, so it's an excited determinant. Now the Cover cluster wave function, of course, is e to the t acting on SCF, which means the e to the t and the e to the minus t goes out, while the product of both gives 1. And then I just have the SCF wave function in the bra and in the cat, and a de-excitation operator, which then means that I have the overlap between SCF and an excited determinant, and that's of course 0. Now all these equations, they can be written in this way. So we have our Cover cluster wave function, then we have the Hamiltonian, we have e to the minus t, and we have an excited determinant, and the right-hand side, as I just explained, is 0. These expressions here, they're also called the Cover cluster vector function, and identified with what kind of excitation we're looking at. Now let's look at the expression for the energy and for the amplitude equations for the CCSD model. Now in the CCSD model, we have only T1 and T2 operators. So if we have our CCSD wave function, the Hamiltonian, we pre-multiply with e to the minus t, and then with the Hartree-Fock determinant, which means that the t here, and in the Cover cluster wave function is just t1 plus t2. Now, in order to let the exponential operator act on the Hartree-Fock determinant, we have to expand it in the normal CS expansion of an exponential. And if one does that, then one arrives finally at this expression where we get the Hartree-Fock energy plus this correction where we have Hartree-Fock at both ends, and then we have double excitations here, the T2 operator and T1 squared, because of course if one expands the exponential, one gets different powers of what the exponent was. So we get, for example, T1 squared or one half of T1 squared, and we have the fluctuation operator here. And these are the only ones which survive, the only terms which survive because of a Brion theorem, and then of course the Slater-Connon rules. Correspondingly, for the amplitude equations, we have again this CCSD wave function in the cat, the Hamiltonian, then we have pre-multiplied with e to the minus t, which here is then e to the minus t1 plus t2, and then single excited or double excited determinants. And if one also expands the two exponentials again, then one ends up with an expression which looks like this for the single amplitudes equations, and for the double amplitudes equations like this. And in order to make the notation a bit shorter, I have introduced what is called the T1 transformed operators in this form, which is very much like the kind of transformed operators as we had it in the interaction picture, which we have here. Here we have the fluctuation potential T1 transformed in different places. What one should notice is that in the equation here for the single amplitudes, which essentially is the equation from which one would like to determine the amplitude corresponding to this single excited determinant, so it's a TIA. But this equation here has the full T1 operator. So I have a sum over all the other T1 amplitudes. And I also have the T2 operator, which means I have a sum also over all the T2 amplitudes. And correspondingly, in the same way in the doubles equation, I also have the T1 operators in here, in this T1 transformed fluctuation potential, which means that not only does the single equations depend on all the T1 amplitudes, although it's just an equation for one particular, but it also depends on all the T2 amplitudes, which means all these equations are coupled to each other. So the amplitudes equations are actually a set of nonlinear coupled equations, which one has to solve iteratively. And this can become rather expensive already. So one has many equations for the doubles amplitudes, and one, based on perturbation theory arguments, keeps only the lowest order terms in these doubles amplitudes equations. An approximation to the CCST, which is called the CC2 model, which is based on an perturbation theory analysis of these equations, and in particular of more or less like a Möller-Placer perturbation theory, with the only difference that the single excitation operators, so the T1 operators, which in Möller-Placer perturbation theory enter into the second order wave function. So single excitation are second order, but here in these couple cluster models, they are treated as first order. The reason for that is that these models, CC2 and also CC3, were developed not only for calculation of grounded energies, but in particular calculation of properties like response functions. And as soon as we have an external perturbation included in the system, then of course single excitations will no longer be second order, but they actually already enter the zeroth order wave function. So therefore are treated as first order. The double excitation operators are first order, like they are also in Möller-Placer perturbation theory. So if one looks at the CC2 amplitude equations, the equations for the single excitations, they are the same. It's the equations for the double excitations which are reduced or which are approximated compared to the CCSD equation. And the term which vanish are the ones which include commutators of the fluctuation potential or the T1 transform fluctuation potential with the T2 operators, because they would then be higher order than the terms which we have here, which is the Hartree-Fock-Hamilton is zeroth order, the T1 is first order, and this T1 transform fluctuation potential is also first order. Now the next higher level is then CCSDT, where also the triple excitation operator is included in the wave function. This is rather expensive method, and it's not yet really used on a regular basis. There's a similar approximation to CCSDT as CC2 is to CCSD, and that method is called CC3. And again, what one does, it's the amplitude equations for the highest level of excitations, which in this case would be the triples excitations, are again approximated similar as it's done in CCSD. However, if one uses CC3, one still has to solve iteratively amplitude equations for the triples, which is still expensive. Now, an alternative way to approximate CCSDT is by a method which is called CCSD parenthesis T, which is what one could say a non-iterative alternative, because CCSD parenthesis T is essentially a CCSD calculation where the single and double excitation amplitude equations have to be solved iteratively. But for the triples amplitudes, one does not solve iteratively couple cluster equation, but one uses the expression from Möller-Placer perturbation theory. In fourth and author, one has an expression, as we had it discussed in the chapter before, for the triples amplitudes to the second order wave function correction, and one uses these expression and then just uses the couple cluster single and doubles amplitudes in order to evaluate them. And actually one includes also two more terms from fifth order, which correspond to the coupling between singles and triples, because they come as no extra cost. And that is the very popular CCSD parenthesis T model, which very often is called the golden standard of quantum chemistry.